It happens. This is the first time anyone's ever been tired here?
Very first time.
Yeah, because usually this class everyone's so lively, yeah. I will say I've seen fewer people just like straight up fall asleep in this class than my night class. So that's, I guess that's good.
Fewer people fall asleep in this one?
Yeah, I think so. But I understand. If you need to put your head down, go ahead. All right. So, yeah. This is, that's a good question, because they changed it. 10. Acids and bases. And this will be the lab on Tuesday. We'll do acids and bases. So you'll see some of the stuff that might help a little bit. All right. So last time we talked about. Oh yeah, sorry.
There is like an extra sheet with the next lab.
An extra sheet.
It's like an extra credit problem, I guess.
Oh, that's new. That's not from me.
Okay.
That's like a general course thing. Don't worry about it. Just do the basic lab. Yeah, I'll delete that this afternoon. I forgot. Yeah, anything else? Any questions? Okay. All right, so we talked about equations of acids and bases like this, and we looked at conjugate acids and bases differing by a hydrogen ion. So today, we're going to go a little bit more into what makes something an acid or a base in practice. Like if we actually have a sample of it, how do we know if that stuff is an acid or a base? So to do that, get my notes to start here. To do that, we're going to look at this idea of pH. Has anybody heard of pH before? Where have you heard that used? In what contexts?
I don't know if this is relative, but like pools, like chlorine pools, like.
Oh yeah, like so you gotta check the pH of
level.
your pool, because if the pH is, you know what it's supposed to be. I don't know much about pools.
Oh, got it. I just remember the strips. It needed to be orange.
Orange. Okay.
I don't remember the level now.
That's totally right. And I think, and what we'll on Tuesday we're gonna do a lot of pH measurements, and one of the ways we measure it is by color, because it's easy to like test it and just see what color it is. Yeah, so pools are example. Soil, has anybody ever tested their gardens for pH? Because you have to, certain things grow better in one type of soil or another. But it's basically a measure of how acidic or basic something is. And we're gonna be a little bit more precise about that because this is chemistry. So we're gonna look at what happened in pure water. This is a really weird reaction, but bear with me. What happens if water reacts with water? What would you say is probably happens here?
It forms a bigger water.
It's a good guess, yeah, or just nothing, because it's the same thing together, and we don't really think of water reacting with itself. But there is one way in which water can react with itself, and that's in an acid-base reaction. So two water molecules can react as acids and bases. And let's just pick, because it doesn't really matter. Let's say this one's the acid, and this one's the base. So using the rules that we looked at on Tuesday, when an acid-base reacts, let's just remind ourselves again, when an acid and base react with each other, what happens?
The hydrogens transfer.
Yeah, hydrogen transfers from what to what? Anybody remember? Which one loses the hydrogen, which one gains the hydrogen?
Acid loses it.
The acid loses it, the base gains it. Right? So the acid loses a hydrogen ion, the base gains a hydrogen ion. So based on that definition, can you draw the products of this reaction? If one of those water molecules acts as an acid, and one of those water molecules acts as a base, what happens? You got some stuff down. So what's one of the molecules that you picked for something that forms?
Hydroxide.
Hydroxide. Okay. Hydroxide is the result of one of those water molecules losing its hydrogen. So if that one that we called an acid loses a hydrogen, what's left over is hydroxide because it's missing an H, and its charge is now -1 instead of 0. It's just lost that positive charge. So then the other thing must be hydronium ion. We talked about hydronium ion on Tuesday as this water with an extra H plus on it. And hydronium ion is the source of acidity. We kind of mentioned that that was important. Hydronium ion is what makes things acidic. The more hydronium ion that's there, the more acidic something is, the more we call it an acid. So when we measure acidity, what we're really measuring is how much hydronium ion is there. So we're going to measure, because it's in solution, we're going to measure it as a concentration. Rather than like grams or something like that. We're going to use a molar concentration, and that's going to give us our acidity. So in pure water, the concentration of hydronium ion, and the way we express that concentration is by putting that in brackets like this. And the value for it in pure water is 1 × 10⁻⁷ molar. And we looked at scientific notation a couple times briefly this semester when we looked at moles, and then back at the beginning of the semester when we were talking about units and things. But what that means is a number like this, 0.000001 moles per liter. So that is a very, very small concentration. That is a tiny, tiny, tiny number. And in most cases, when we talk about concentrations of acids, we are dealing with these super tiny numbers. So this pH scale was developed as a way to not have to deal with these tiny numbers all the time. So pH is defined as the negative log of the hydronium ion concentration. All right, so this is probably going back a little ways, but who remembers logs? Yeah, that's pretty much the looks I usually get at this point in this class. But you've heard of them. It's at some point in your life, you push that little button on your calculator for some reason, right? Everybody sort of vaguely remembers having doing that. Yeah, maybe it was by accident. Yeah, it's called a logarithm, and we're not going to go into the whole theory of it. We can push our buttons on our calculators, but actually we're going to be even simpler than that. We're not even going to need to push our buttons on calculators. A logarithm just simply tells you what is the exponent. What is this little number up here? So the different color here to keep organized. The log of some number where it's 10 to some power up there simply is that power thingy. And it has to be a 10, but since we're dealing with numbers with scientific notation, it's always going to be a 10, so that's fine. There's other kinds of logs that have different bases. We're not going to worry about those right here. So that's pretty simple. That means that if we want to know the pH of pure water, all we have to do is take the negative log of the hydronium concentration, which is 1 times 10 to the minus 7th. Based on that definition I just told you, what's the log of 1 times 10 to the minus 7? Yeah, it's just, well, it's actually minus 7. So the log is minus 7, but then there's this extra negative out there that flips it. So if we evaluate that entire expression, we have negative 7, which is positive 7. So that tells us the pH of pure water, excuse me, is 7 based on the hydronium ion concentration. And I think 7 is a much nicer number to deal with than 1 times 10 to the minus 7. And I like that we can just say 7 instead. So that's really the whole reason for the pH scale, that we don't have to think in these powers of 10 every time we're talking about acidity. We can just have this nice scale that goes from about 0 to about 14. The reason for those limits is because if we, again, think about these acid-base reactions that we've talked about before, what's going to happen is when you have more acid, more hydronium is going to be generated in solution. If you have more base, less hydronium is going to be generated in solution, and more hydroxide is going to be generated in solution. So there's always this back and forth between generating more hydronium and generating more hydroxide. And so that's why the pH has this specific range. So let's practice this a little bit. Getting back on here. Here, let's use those brackets. So there's our basic equation. Now, I'm going to make a little table and make up some numbers where one column is going to be our hydronium concentration. One's going to be the pH. And one, we're going to decide if this is acidic, basic, or neutral. All right. So I'm going to put down some things in different areas of this table, and then you'll work together and try to fill in the rest of it. Okay, so you've got 2 concentrations and 2 pHs. See if you can fill in the rest of it, and then decide if it's acidic, basic, or neutral. Now I haven't given you specific definitions for acidic, basic, or neutral yet. I want you to see if you can figure that out. I'm going to give you one more too. I'll take a couple minutes with that. Flag me down if you have a question or if you're stuck. If you're not sure on some of these, especially with the acidic, basic, or neutral, give it a try, take a guess, maybe put your guess in parentheses or something to show that you're not quite confident about it. And then we'll talk about it. Okay. All right, so that first one, 1 times 10 to the minus 13. What's the pH? 13, yeah. Just take that little number, 13. If the pH is 4, we'll go to the acidic, basic, neutral in a minute. If the pH is 4, what's the hydronium ion concentration?
1 times 10 to the negative 4.
Right. And then if it's 1 times 10 to the minus 2, what's the pH?
2.
2, yep. If the pH is 12, the concentration is? And if it's 1 times 10 to the minus 6? 6, yeah. See, I told you logs were easy, right? Super. You can go to your math teacher and say, well, it was easy in chemistry, so I don't know what your problem is. Don't actually do that. That's not nice. Okay, so looking at these then, let's decide if they are acidic, basic, or neutral. How do we decide that? What's going to be our criteria for deciding if something is acidic or basic, would you say?
Well, something is neutral and everything smaller than that is acidic and everything greater than that is basic.
Okay, why?
Oh, I just remember it because of the burn. Like, oh, you think you're a 10? Yeah, on the pH scale because you're basic. That's
Oh, okay. I hadn't- That's good. Okay, that's a good way to remember it. Nobody has ever burned me in that way. That's
It's
good.
a good way to remember.
Maybe I'm not too basic. Yeah, it's a good way to remember. As long as you remember that it's a 10.
So that right? 10.
That is right, but that's not like the dividing line. It's just the 10 is in the basic. So okay, so we've got our scale, and you're absolutely right that below 7 is going to be acidic and above 7 is going to be basic. So why? What is special about those two ranges that would make something more or less acidic? And instead of talking about acidic and basic, let's just think about acidic. What makes something more acidic? Giving away its ions. And what's evidence of that in solution? We go back up to this equation as a hint here. What happens in a solution that has more acid in it? What do we have more of? Yeah, hydronium. So we have, if that hydronium is the source of acidity, when we have more of it, we have something that is more acidic. So let's go back and look at these numbers. Well, if pure water has a concentration of 1 times 10 to the minus 7, is 1 times 10 to the minus 13 a larger or smaller number than 1 times 10 to the minus 7? Smaller, yeah, because that's like 0.00000, a few more zeros before the 1. So it's, what, 100,000 times smaller. So that means there's 100,000 times less hydronium ion in that solution than in a neutral solution. And if there's that much less hydronium ion, there must be more hydroxide ion, and that must be more basic. Does that reasoning sort of sit okay with you? If there's more hydronium, you're going to get a smaller exponent, and that's going to make more acidic. If there's less hydronium, you get a larger magnitude of exponent, a more negative exponent, and that's a smaller number, so that's more basic. Okay, so now we should be able to classify these things. We're going to call this one basic. Acidic, right? Acidic, basic. And then that last one, it's kind of in the middle, right? It's not too far away from 7. So depending on the scales that you're looking at, sometimes they'll say, well, 7 is neutral, and anything that deviates from 7 is acidic or basic. Sometimes they'll say, well, it's more like 6.5 to 7.5. Sometimes it's like, well, it's more like 6 to 8. I think this still counts as in the neutral range. So I call this neutral. You don't have to. If you want to call that acidic, that's okay. But I think 6 to 8 makes a little bit more sense. We'll talk a little bit about blood in a bit. Blood's pH is between 7.35 and 7.45, so that's a little bit on the higher scale. When we talk about waste management, things like that, sometimes then there's like a range where it's neutral enough, that kind of a thing. So we might call this slightly acidic. These are qualitative kind of judgments based on the application that we need. So I would not give you a multiple choice question that said, if the pH is 6, is it A acidic, B basic, or C neutral? Because, you could make an argument either way. So if I did do that, you could just come up and be like, Joe's question's bullshit. That is not, there's not a good answer here. So I won't do that. All right. So we have an idea about this now. Let's look at some things. There's a nice table in the book of some examples of acids and bases, so you get a sense of what those things are. And I will just steal their beautiful picture here. So let's look at the acidic neutral side of the spectrum first. So way up at 0, you have a 1 molar HCl solution. A 1 molar HCl solution has a pH of 0 because the log of 1 is 0. How do we know that the log of 1 is 0? I mean, we could use the calculator. But what's 1 in a power of 10? No, I'm really asking you to remember some math, so I'm sorry. What can you take 10 to the power of to get 1? 0, yeah. So 1 molar is 1 times 10 to the 0 molar. That's 1. And so that's our pH of 0. Then we've got things like gastric juice, which is your stomach acid, which is also mostly HCl, I think. And lemon juice, right? Really acidic stuff, vinegar. Carbonated beverages, like, that doesn't just mean from the carbonation. Carbonated water is not quite that acidic, but that's like Coke and Sprite and those kinds of things. Oranges, apple juice, tomato, coffee, pretty much everything we eat is going to be on the acidic side of the spectrum. The basic side just doesn't taste that good. We talked a little bit about that on Tuesday. On the other side, there's not quite as much there. But we're going to see more things like cleaning stuff. We've got seawater is slightly basic. This is antacid, milk of magnesia, ammonia, bleach, lye, which is like drain cleaner, sodium hydroxide. We talked about pretzels on Tuesday. That's like the only kind of basic food because one of them because the bread is boiled in lye to give it that nice brown. That's a chemistry thing too. I don't know. Does anybody know about food science stuff? About that for a minute. The browning reactions that happen when you cook. Like if you cook something and it kind of turns brown and gets like really delicious, like frying, like the outside of a French fry, right? Or yeah, bacon or like any kind of meat or vegetables that you grill or cook in the pan until they kind of brown up nicely, that kind of stuff. Those are chemical reactions between proteins and sugars, so between amino acids and sugars, and they are somewhat pH dependent. So at a higher pH, those reactions can occur at a lower temperature. Those are called Maillard reactions. And so those reactions can occur more easily in a more basic medium, and that's why sometimes things like baking soda will be used for that. There's a neat trick if you eat meat, stuff like chicken, if you rub the skin with baking soda, a little bit of baking soda, and let it sit for like a day, then when you cook it, it'll be extra brown and crispy and delicious because of the pH-mediated browning reactions. So you can try that. It's also why you get really good flavors in a pressure cooker, because you have a little bit higher temperature. That's not the pH reason, but you have the higher temperature, which can better mediate those reactions. Sorry, it's a little off topic. Speaking of off topic, I really don't understand that basic insult. What does that mean? Can somebody?
Oh gosh.
Like, I have a sort of a sense of it, but not like a
Basic,
clear
like,
definition.
The Ugg boots and the black North Face with the white iPhone and the pumpkin spice latte and the straight
So
hair.
it's a particular
It's like,
set of cultural identifiers.
yes.
But why is it an insult then?
Normally, people who are basic don't have original ideas, or they just kind of.
Okay, so it's an
follow-
insult based on like a lack of individuality.
Yeah,
Yeah,
'cause
you're
they're
not fun.
basic or they're
Okay.
basing their persona off.
It's like calling someone a loser.
Kind of,
It
yeah.
seems different though,
Yeah.
It is.
because yeah,
It's
I haven't been
more-
called. I've been called a loser a lot more than
Basic.
basic.
You should Google basic girls, and then you would understand that.
You might get more if you Google basic bitches, but.
Okay.
Or basic white girl, but that's
Yeah.
kind of prejudice.
Okay.
It totally
kind of
is. It's
racist.
awful, but it's
All right.
a thing.
I'll probably not do that at work. But I also feel like there could be some really like the results of that search could be things that you don't want to find. But no, yeah, I don't know. Okay, well, thank you for the information anyway. All right, so the point of that, okay, we have some references now for acidity, and now we can actually put a couple extra columns in our list here, and that is the hydroxide ion concentration. And what we call the POH, which is just like the pH, but for the hydroxide ions instead of the hydronium ions. Let's see if we can figure out how to fill these columns in based on what we've already done. We look back up at this reaction. Pure water reacts with itself. We make hydroxide and hydronium. Which one do you think we make more of in that particular reaction? Hydronium? Yeah. No, it's a trick question. You make the exact amount of both because you have water and water together. There's nothing that favors one over the other. So you end up having an even amount of hydronium and hydroxide formed in pure water. So how much hydroxide is formed in pure water? Or what is the concentration of hydroxide in pure water?
7?
Yeah, or like 1 times 10 to the minus 7 molar. So let's see if we can fit that in here. Concentration of hydroxide or hydronium is 1 times 10 to the minus 7 molar. So the concentration of hydroxide is also one times 10 to the minus 7 molar. Because they're the same. They have the same concentration. Because the hydrogen has to go from one molecule to the other, you always have to make the same of each, the same concentration of each. All right, so that gives us a clue, and it tells us that anytime we have one of them, we can also figure out how much of the other one we have. Because if one goes up, the other one has to go down the same amount. So what's 7 plus 7? Okay, so you remember some math. That's good. So then what do you think is if the pH is 13, what do you think the POH has to be? What? 1, yeah, right. The POH and the pH have to add up to 14 because the two concentrations are dependent upon each other. So if the hydronium concentration is 10 to the minus 13, the hydroxide concentration has to be 10 to the minus 1. And those exponents have to add up to 10 to the minus 14. All right, so see if you can fill in the rest of this table now. Oh yeah, there was one more picture I want to find. Go ahead and do that. I'll find this picture while you do that. This one. Okay, we'll finish that up. So we always make sure those things add up to 14. So that means we're going to have like this. And we can then have this POH, which is the same technique done to the hydroxide concentration, and gives you something like that. Is that what you got? Okay, good. That's a really important tool because based on what we are doing, like in the lab, we may not easily be able to measure both of those things. So if we want to know the pH, sometimes it's easier to know the hydroxide concentration and then to calculate the pH from that. Sometimes it's easier to calculate or to measure the hydronium concentration and then calculate from that. So we'll do a little practice where we look at both of them. But as we're talking about this, I forgot to show you this chart before. This is around Halloween. This is kind of interesting. Did you know that candy is bad for your teeth? I don't know if anybody's heard that before. Hopefully you have, but it is. The reason candy is bad for your teeth, it's not just the sugar, it's the acidity. So below a pH of about 4, the enamel of your teeth can start breaking down, or it does start breaking down, and bacteria can start digesting it and processing it. And so this was from a study from University of Alabama, Birmingham, where they measured the pH of the saliva in your mouth after eating a certain amount of these different foods and figure out what the pH was. And so you can see that all of these sour candies, even ones that you don't necessarily think of as really sour, like Laffy Taffy or Starburst, some of these I do think of as sour, but they're really, really acidic, right? Almost getting down into battery acid realm, which is sulfuric acid. So yeah, that stuff's bad for your teeth. Because of what it does, or it allows the enamel to break down at that low pH. Does anybody know how you can still enjoy these sorts of foods, but not lose your teeth too much? It is possible. The trick is contact time. In other words, the longer that your mouth stays at that low pH, the more your teeth are subject to that enamel breaking down. So if you like just eat a giant bucket of Sweethearts, what's a good sized bucket of Sweethearts? This maybe. If you can eat that all in like 10 minutes or something, then you're probably okay. You know, you can have some water, your saliva will rebalance that pH in your mouth. You probably won't feel great for other reasons because you just ate a giant bucket of Sweethearts, but your mouth will return to a more neutral pH. But if you've got a big bucket of Sweethearts and you're snacking on like one Sweetheart every couple minutes for a day, that's when you have trouble because your mouth stays at that low pH all day. And that's why things like Diet Coke are really bad for your teeth. Even though it doesn't have sugar, if you're like slowly sipping Diet Coke throughout the day, you're keeping your mouth at that low pH for a significant amount of time. All right. Okay, so let's take a look at, before we go on to the next topic, let's take a look at how we calculate pH. And we'll also look a little bit about how we can use our calculators when it gets a little bit more complicated. All right, let's do this. Let's just take some more. Okay. Let's determine the pH for the following solution. So that first one, part A, is like what we've just been doing. So if you see a hydronium ion concentration of 1 times 10 to the minus 8, what's the pH? 8. Yeah, if you look at that exponent, it's just 8. B is not quite so simple. because of that 5 out in front, we no longer just have that 10 to the something. So this is where we would use a calculator to figure out that logarithm. Depending on your calculator, this can be done in a couple different ways. Let's see, does anybody have some calculators? Let's try some different calculators. So maybe, does somebody have a graphing one and then like a simpler one? Graphing. Everybody's got fancy calculators, right? Okay, so if you haven't done this in a while or ever, let me show you what this looks like on a calculator. And just so we have it, let's remember our number is 5 times 10 to the minus 2 whole. Okay, so we got to figure out the pH of something with hydronium concentration of 5 times 10 to the minus 2. All right, calculator. Weird light reflecting on it or something. That's worse. Okay. Okay, these types of calculators use direct logic, which means you just kind of type the thing in exactly as you would write it down. So I'm going to write, you can see both things at once here. Almost there. Okay, that's really good. All right, so I'm going to write the negative log, and then I want 5 times 10 to the minus 2. Best way to do that on these types of calculators, instead of typing in all the times 10 to the all that stuff, is to just go 5 and then use this little EE. You have a little key that says EE, that means times 10 to the, and then we can write negative 2. Okay, and we see that our pH is going to be about 1.3. Thanks. pH is 8. pH is 1.3. Okay, so the next one, now we have a hydroxide ion concentration. But again, it's not a 1 times 10 to the something number, it's 3.5, so it's going to be one of these in-between ones. So does anybody have a simpler calculator to do this with today? Okay, I'll just use the one on the screen. If you're using a kind of calculator like this, you just can't do it. But as long as you have a few more functions, you can. Now this kind of a calculator, which is more like a typical scientific calculator, you're supposed to put the function after you put the number in. So you don't put the log first, you put it later. So I would go 5 times, oh, I can't even do that here. Hold on. In this case, I'm going to want to translate that because this isn't going to do a great job of scientific notation. So 3.5 times 10 to the minus 4 is 0.00035 because I go 1, 2, 3, 4 to get to 3.5. And then I'm going to push the log button and then flip the sign because of the negative. So 3.5, about 3.45. So we'll say 3.5. All right, now we don't have the answer yet, right? Because the question is asking for the pH. So if we found the pOH, can we find the pH? What's the pH? 10.5, right. So we're going to subtract from 14 because the pH and the pOH always have to add up to 15, or to 14, sorry.
I'm sorry, it's negative log, and then you type in the number E, and then what?
The exponent, just the exponent, so just minus 4. So you may come across some of these things in the homework, and that's how you do it, or if you want to check some of the other ones that you've done by hand, that's fine. You won't have these types of calculations on the exam because we don't require everybody to have a calculator that's capable of that. So you'll only see the easier numbers that we've already done on the quizzes and exams. And then for this last one, this is another thing that can confuse you, is if you see the number is not written in scientific notation, in this case, it's not really helpful to put it in scientific notation because you got to use a calculator anyway. But let's say that instead of 0.005 molar, that's one that you should be able to do without a calculator. But the way to do that without a calculator is to convert this into scientific notation. So what is this number in scientific notation? Anybody do that?
1 times 10 to the negative 3.
Yeah, that's going to be 1 times 10 to the minus 3. The way we do that is you just count the decimal places from the decimal to the number. So 1, 2, 3. And so that tells us it's 10 to the minus 3. Now that we see it as 10 to the minus 3, we can say, okay, then the POH has to be 3, and the pH has to be 11. Once we see it in that scientific notation form. All right, so now let's answer that other question. Looking at these, what?
Would it be backwards? Oh, I'm sorry. Oh, never mind. It's not backwards.
Okay, yeah, because the OH concentration
The
is
OH,
given.
yeah.
Yeah. So we've got POH, pH. Make sure you watch for that on quizzes and exams. It's just one letter. It's just an O, but if it's there, it means, it changes everything. So if I say, is this solution with a POH of 3.5 basic or acidic, you might, in the stress of an exam and all that, say, oh, 3.5, that's less than 7, it's acidic. Make sure you're watching for that OH, because really that would be an example that it's basic.
How did you get from the 0.005 to the 0.001?
I just crossed it out and picked a different number instead.
Oh, okay.
Yeah, it has nothing to do with that 0.005. Sorry. Because if it were just 0.005, we'd have to still use our calculator to get that number. All right. Okay, next thing we're going to talk about, going to take us through the end of class here is, oh, there we go. Here's being a little overtaxed here. Okay. Buffers. Has anybody heard of this? What have you heard of it? What is it for? Or where have you heard it before?
Doesn't it kind of prevent the pH from changing too quickly?
Yeah, a buffer is something that prevents the pH from changing. What would make the pH change quickly? Like, would it just happen naturally, or is there one specific thing happening that this is preventing the pH changing from happening? Sorry, I'm being kind of big. I should just tell you. Buffers prevent or lessen pH change when strong acids or bases are added. So you said they're a solution that you can add an acid or base to without changing the pH. And I just realized we skipped a thing because we haven't talked about strong acids and bases yet. So let's do that first. We'll come right back to that. What does it mean when we talk about a strong acid or a strong base?
Extreme.
Extreme what?
On the scale.
Like the pH? Okay, that can be part of it, yep, that strong acids tend to produce a lower pH at similar concentrations. Does anybody know why that is? Like, what is it that they're doing that's different? The word strong in strong acid refers to the fact that it is a strong electrolyte. Remember that word electrolyte from our last chapter on solutions? What is a strong electrolyte?
Something that will dissolve or disassociate completely.
Yeah, something that dissociates completely or creates ions, dissociates into ions in solution. So a strong electrolyte dissociates or breaks apart completely in solution. So when we did that light bulb experiment where you saw the light turning on in some solutions and not in others, that was because a solution like sodium chloride, the sodium and chloride ions completely break apart, allowing the current to move through that solution and for the light to come on. So a strong electrolyte dissociates into ions completely in solution. And so a strong acid is that. It is a strong electrolyte. It is an acid that breaks up completely in solution. And there's only a handful of them. HCl is one. Nitric acid. Sulfuric acid. Perchloric acid. Bromic acid, and iodic acid. That's all the strong acids. And you only need to know 3 of them this class, which is hydrochloric acid, nitric acid, and sulfuric acid. Those are on the objectives on Blackboard that you need to know those 3. So these are examples of acids that when dissolved in water, break up completely. That means that if we have, let's say, HCl plus water, we have created hydronium ion and chloride ion. And notice now what my arrow is doing. Instead of having a back and forth, I'm all forward. So when HCl goes in water, there's really no HCl molecules sticking around. It's all dissociating into ions and making hydronium and chloride. And that's the case for all of those examples right there. Any other acid that's not one of those is called a weak acid. If we did the same thing with, let's say, HF, which is a weak acid, hydrofluoric acid, we make a little bit of hydronium and a little bit of fluoride. But look how I've drawn those back and forth arrows. Most of what happens is the HF just sits there. It stays together. H and F stay stuck together dissolved in that water. So they dissolve, but they do not break apart. It goes into the water surrounds the molecules, but they don't break apart. And that's a weak electrolyte. Okay, now, this is the big thing that everybody gets confused with. Those words strong and weak do not apply to other characteristics of the acid. So we always want to think of strong acids as like dangerous things that will burn us, and weak acids as not dangerous things. And that's not true at all. And these are good examples of that. HCl, hydrochloric acid, if it's really concentrated, yeah, it can burn you, but I mean, our stomach acid is HCl too. So it's not like that bad of a thing, especially at lower concentrations. HF is super bad. HF can dissolve your bones. HF can eat through walls. HF you can't even keep in glass containers because it will eat through the glass containers. So you have to keep them in stainless steel or plastic. That is like the nasty cartoon style acid that can just eat through anything. Yet we still call it a weak acid because it's weak in that it doesn't dissociate into ions. So the strong weak thing doesn't have anything to do with corrosiveness or poisonousness. I don't know if that's a word. Poison.
Toxicity?
Toxicity? Yeah, that's probably better. Yeah. It just has to do with what it does in solution. Does it break apart or no? And so as an example of that, There's a nice picture in the book here. We don't need to copy this one over. Take a look at these two solutions. The acid has the formula HX. As big as I can make it. Which one of these solutions represents a weak acid and which one represents a strong acid? How can you tell?
B is the strong acid,
How do you know the B is a strong acid?
because they're disassociated completely.
Yeah, so we see that in B, you've got all kinds of ions. You've got X minus, H3O plus, lots of different ions there. In A, the HX are all together still. Not all of them. There's a little bit of ions, but most of them are still together, still neutral. So that tells you this is weak acid, this is a strong acid. Doesn't tell us anything about which one we want to get on our skin or whatever, probably neither, but it does tell us how they break apart in solution. And so that has implications in concentration, like and pH. So if we go back to our strong acids versus weak acid over here. So that means if we put 1 mole of HCl into a liter of water, we've got a 1 molar solution, which since it's all breaking up, that also makes a 1 molar hydronium ion solution. 1 molar hydronium ion solution has a pH of 0, so we know our pH is based on how much HCl goes in. With HF, that's not the case, because even if we use 1 mole of this, we don't make 1 mole of this. We make way less than a mole of that, because it doesn't break up enough. So we can't know that easily what the concentration is going to be. We have to like do some experiments or look some stuff up on some tables. It's a whole different thing to try to figure out what the pH of a weak acid is going to be. Strong acid, it's easy. However much you put in, that's just how much hydronium is in there because they break apart. Weak acid, that's not the case. So that's the implications for that. Okay, then on to buffers.
What about
Yeah.
bases?
Oh, good point. So bases, yeah, we can talk about that. Bases have to do with solubility. So all bases are going to be, not all bases, but many bases we're going to see are going to be metal salts of hydroxides. So things like sodium hydroxide, calcium hydroxide, that kind of stuff. Magnesium hydroxide. Metal salts of hydroxides. And those are pretty much all strong bases. They dissociate in solution into ions. Now, there are some hydroxide salts that are not very soluble, and those would be weak bases. You don't have to know about them. One of the weak bases you should know about, though, are other kinds of bases that are not hydroxide salts, like ammonia. Ammonia is a weak base. And it actually doesn't dissociate at all in solution. What it does instead, we looked at on Tuesday. Yeah, here. When ammonia goes in water, it makes ammonium and hydroxide. So it actually makes hydroxide ions in solution. And that's what makes it basic. Even though NH3 doesn't look like a hydroxide, and I mean, it's not a hydroxide, when it dissolves in water, it makes hydroxide, and that's what makes it a base. But it doesn't make, like all hydroxide, so that makes it a weak base. It doesn't totally make ions. And that's really all we have to look at about bases. So if you see metal salts of hydroxides, those are usually bases. Ammonia, and we talked about this on Tuesday, something like ammonia can be an acid or a base depending on what reaction it's in. We call it a weak base because it usually acts as a base. When it's in water, it's a base. In other stuff, it can be an acid, but it usually acts as a base. So we call it that. Okay, let's look at buffers. I want to pull this picture from the book because rather than draw it. We'll kind of do it in two sections here. So here's what a buffer does. Let's say you measure the pH of water, and we're going to use pH meters like that next week. Let's say you got some pure water, and you measure the pH, and it's 7.0, as it should be, right? Now you're going to add just a couple drops of acid, hydronium or hydrochloric acid, some source of acid, just a couple drops. You add a couple drops of acid, all of a sudden that pH goes way down. Because a few drops of acid increases the moles by a significant amount. And since we're talking about the 10 to the minus whatever of moles, of molarity, those few drops in a little beaker are actually going to make a big difference in the hydronium ion concentration. They're going to increase that hydronium ion concentration quite a lot. And so that's going to drop the pH a lot. So just a couple drops makes the pH go from 7 to 4, or it could even go lower. Same thing on the base side. You add a tiny bit of sodium hydroxide to pure water, suddenly your pH is way up at 10.5. And I mean a tiny bit. I mean like a imperceptibly small amount. Like if you took a tiny grain of sodium hydroxide and you dissolved it in water, that pH would jump up to about 10.5. Because remember, we're dealing with these tiny concentrations, 10 to the minus whatever, 0.000001 moles per liter. Okay, so that's how water works. Now let's look at how a buffer works. Or what a buffer does. It's not really how it works. Uh-oh. Broke it. All right, so now let's say instead we have a buffer at pH of 7. And buffers can be designed. If you go on and take more chemistry, you'll learn how to build a buffer with the right pH. But you can build a buffer with any pH you want. Let's say we want a buffer that has a pH at 7. If we do that same experiment, we add acid to it, the pH changes, but only a little bit. So instead of dropping down to 4 right away, it goes to like 6.9. If we add hydroxide, instead of that pH going up to 10, it goes to 7.1. Now, if we add enough acid or enough base, eventually that pH will start going way up. But it's going to take quite a lot, and certainly a lot more than if that were pure water. And so this is how buffers work. They resist the change in pH when more acid or base is added or generated. The mechanism for that is a little bit complicated, and we don't really need to go through the whole business of it. They do talk about it in the book. Oops. We'll kind of just describe it in general here. A buffer is made from a weak acid and its conjugate base. So their example here is acetic acid, and then acetic acid loses that hydrogen and becomes acetate ion. Remember losing the hydrogen, creating the conjugate base we worked on Tuesday? So that's what a buffer is. It's a mixture of those two things. The way that works is, or the way that controls pH, is it has whatever pH it has. If you add strong acid to that, what happens is the hydrogens from the strong acid get stuck onto the conjugate base of the weak acid and give you more weak acid and less conjugate base. So it kind of uses up a little bit of this to make more of this. But this is neutral. So that doesn't affect the pH because that doesn't really contribute to the hydronium ion concentration. It doesn't break apart and make more ions. So in that way, you've kind of absorbed some of that hydronium and stopped it from changing the pH by kind of trapping it in the weak acid, trapping it in the acetate ions, or in the acetic acid. On the other side, we can do the same thing. We can add hydroxide, and then we end up with less of the weak acid because it pulls some of that hydrogen off of the acid and makes water instead. Water and acetate. So again, you're still not generating more hydronium. And if you're not generating more hydronium and you're also not taking away hydronium, then you're keeping the pH right where it should be. And that's the job of the buffer. Most important buffer probably to us is blood. Blood pH has to stay between 7.35 and 7.45, or you're in trouble. So if I ask you on a quiz or exam, what's the pH of blood? You can't say 7. Because if your blood is down at 7.0, you're in trouble. That's too acidic. Your body stops working. It's that sensitive. So it has to be buffered to stay in that 7.35 to 7.45 range. Does anybody know what does the buffering in the blood? Any physiology folks? I don't know if they talk about that in there.
Not yet.
Not yet, maybe later. The pH of blood is regulated by carbon dioxide. But when you breathe, or when you do respiration, you create carbon dioxide, and that carbon dioxide reacts with water in your body, your cells, or blood, to make carbonic acid, which is a weak acid. Carbonic acid generates hydronium ion in solution. So we'll number these. First that happens, then carbonic acid reacts with water to generate, these are all equilibrium by the way, going back and forth, to generate bicarbonate and hydronium. All right. And that's the source of acidity in the blood. So remember, hydronium is the source of acidity. So that's source of acidity. So the more carbon dioxide you have in your blood, what happens to the pH of your blood? You get more carbon dioxide in there. What happens to the blood pH? Does it go up or down? Everybody's really feeling that late night now.
Mm-hmm.
So if you have more carbon dioxide, remember we talked about the idea of chemical reactions as like buckets connected by a tube. And if you put more in one, you kind of force more into the other side. That's what's happening here. So if you put in more carbon dioxide in your blood, you force more carbonic acid to get formed. If more of this gets formed, then you push this and more hydronium gets formed. So more carbon dioxide is going to lower the pH. It's going to make it more acidic. And if it gets too acidic, then you're in a condition called acidosis. There's respiratory acidosis and metabolic acidosis, depending on if this is happening because of breathing or because of like liver byproducts and that kind of stuff. And then if you don't have enough carbon dioxide, you lose hydronium, you get too basic, and that's called alkalosis, which is the opposite. There's this great picture in the book here. It's a good question, but it's just a weird picture. That one. It's the one breathing into a flat paper bag, but it kind of looks like she's puking. So, do you know about hyperventilation? When you like start breathing too hard and you get lightheaded and stuff? Let's think about what's happening to the blood pH during hyperventilation. If you're hyperventilating, do you think you have too much CO2 in the blood or too little? Or 2 years? That was weird. Too little, yeah. Why do you have too little if you're hyperventilating?
Getting rid of all of it.
Yeah, you're going like, you're like blowing off all of that CO2. It's not sticking around to get into your blood. So there's not enough CO2 in your bloodstream, and therefore your blood pH goes up, right? You're not creating enough acid in your blood, so it goes up. So you breathe into a paper bag, and the idea of this, which is the answer to this question, is that breathing in the paper bag allows you to not get rid of the CO2 as much because it's trapped in the bag. More recent studies have shown that that's not quite true, that the reason breathing in a paper bag helps is just because it relaxes you and because you're focusing on your breathing, which allows you to slow down your breathing. So it's not really that you're getting the CO2 back, it's just that you slow your breathing down when somebody says, here, take this paper bag and breathe into it, because you focus on it. But the idea is the same, that it has to do with the blood pH and how much CO2 is or is not getting into your blood. Okay, so I think that's it. So we'll have a quiz on this stuff on, we're gonna do Tuesday or Thursday? Thursday? So yeah, sometime next week, so we'll do Thursday. Acid-based lab on Tuesday, so that'll be a little bit more time to practice this stuff. And yeah, we're getting down to the end here.